So I am a gradual typing guy and not a machine learning guy, and somehow I ended up on this. But the first author and the third author are much more the machine learning people, so you won't see many meaty details in this talk. Much more high level view. Anyway, so bugs in C, what's the worst that can happen, right? So I'm running an embedded software system for a rocket, and all of a sudden I have an integer overflow error and the rocket's blowing up, and you might think, all right, well, that was an Ada program, and it wasn't really due to specifically the semantics. But the overall point remains. We write a lot of critical software in C, and bugs are extremely costly. So we want to make sure that we're not having bugs, especially ones that are very avoidable. So let's talk about why C is not the best for being able to catch errors ahead of time. So what does this code do if the file foo.txt does not exist? Basically, it doesn't throw an exception that you have to catch or anything. It sets this special integer variable, error no, to 2. And then you can use this thing p-error to kind of print an error string that tells you that there's no such file or directory later. But basically what happens is that in order to do error handling at C, there's special integer values that are assigned, and you have to know what they are, and you need to handle them properly. And there's not native error handling support in the language, so it's pretty easy for bugs to end up in your code if you don't explicitly check for all these specific integer values, right? So this is like the dark side of bad error handling, where Yoda here is like, lack of error handling primitives leads to anger. Anger leads to hating code. Hating code leads to suffering programmers. And this leads to bugs in the dark side, right? So we don't want this. But really, real bugs have slipped into code due to poor error handling support. So we could consider this function here on the left, where on lines 5, we check if this variable is equal to null and return it. And then in basically our callee code, you can see here on line 4 that we do not check if it's null or not, and we directly pass it to memcopy. And this is undefined behavior, so C is free to do what it wants with this. And this led to a real bug in the Linux kernel and the driver code. So this is just one of those things where because you didn't check specifically for what kind of values you returned, and that there's nothing in the language that forces you to, this bug kind of slips in, and it's really tricky to handle. Okay. So what we want is these error specifications. So I want some kind of documentation or something that lets me know when I'm calling a function, like what special cases of values do I need to handle with these errors, like what kind of error codes are being set. So if I have these, right, then it's a lot easier to handle things. Like if I know that in the last case that 0 is basically an error there, then I know that I explicitly need to check for it to prevent a bug. So similarly here, what I want to know is what are the values inside of this zstream error and the zbuff error, and generate an error specification with some tool that says, hey, if you're calling this function here, then you need to check against -2, which is for zstream error, and -5, which is for zbuff error, and otherwise the zok is some other value. Okay, so this will be very useful for you to have ahead of time to avoid bugs, right? But there's 3 main challenges when kind of trying to automatically get these error specifications for all of your C functions. One is that each project introduces its own idioms to represent errors. So different projects will use different values to indicate errors. So maybe positive integers in some cases versus negative integers in another. So the Linux kernel uses a lot of negative integers, but other things like HTTPD uses positive values to represent errors. The other thing is that error and non-error ranges may overlap in a single code base. So return 0 in some math function might be a valid value based on your math. And return 0 from another function might mean that something went wrong in memory allocation and you need to clean it up. So 0 can indicate basically that you have an error or a non-error in your code base. And then error range kind of varies across projects. So I might be looking at the Linux kernel, like I said earlier, which uses negative integers to represent errors, and then some other code base I go to later might use positive integers. Okay. So the way that we're going to tackle this is some new supervised learning paradigm, and I'll talk about like what kind of feature extraction we did and why we have this novel kind of 2-phase learning approach based on transfer learning, and then finally our evaluation results. Okay. So approach 1 to this problem for automatically extracting these error specifications was to learn a global model, where basically we had a lot of like pre-labeled data for all these code bases to indicate, like in the Linux kernel, where an error occurs versus a non-error, right? And we train it, and then if I did it on a bunch of C code bases, then I could throw it at the Linux kernel and get some error classification, and then later I can use it on HTTPD, right? The disadvantage of this is that we need a lot of labeled data in order for this approach to really scale well, especially across a lot of different projects. So otherwise, I could train a machine learning model specific to each project. So I could go through and basically have a smaller set of labeled data and train a model per project and generate my error path classifications for it and get the error specification specifically for that code base. But this needs per project domain knowledge. So I need somebody who specifically knows how to train a model in the Linux kernel versus a cryptography library versus another application. So either I recruit those people or figure out those code bases myself in order to label the data. Okay, so there's a trade-off here where there's kind of a one-time labeling effort for the global model, but I need a lot of it. Or I can have smaller data labelings, but I need to basically figure out how to label all of these different projects, and I have to do this every time I want to train for a new project to get an error specification, which can be pretty tedious. So the question is, can we combine the advantages of both learning models? And yes, so it's based on this idea of transfer learning, but basically what happens is we have a two-phase learning paradigm, where in the first phase we have this core model that's kind of general across different projects and is based on a set of labeled data that we provided until we felt that it was sufficiently large. And then later what ends up happening is that we go and we use this core model to generate a new set of labeled data that we were very confident in the classification results from this more general core model. And then this is used to then train on unlabeled data so that we have a machine learning model for each project. So we have one for the Linux kernel, one for any other application later that we throw it at. But it's all based on this one core model that we provide, and then basically you're free to just apply it to different models afterwards. Okay. So let's talk about what kind of features we want to look at in C code. Basically we have this set of universal features that's used to train our core model. And so two of these things are semantic features, so things that are related to the dynamic semantics of your programs, which are the kind of return expressions that appear in your code. So whether you are returning a constant directly or whether you are getting a macro or you are calling some other function. And then also the kind of return value is basically like whether your integer value is positive or negative or 0 or vice or something that even couldn't be computed ahead of time. Then we have more syntactic features. Okay, so I have things like how long is the path to this current place that I'm trying to figure out whether an error occurs here or not? How many expression statements did I encounter on this path? How many number of function calls, if conditions, etc. Right? And these are more syntactic features in that like these are a little bit arbitrary and I could add dead code or whatever and it wouldn't change the semantics of my program, but it will change the syntax a lot. So the question is, why are these syntactic features kind of useful? And so my explanation for this is that just like this XKCD comic is saying, is basically like the style and the look of your code matters. So we have all these things like style guides for different languages and style guides at different companies. And these are meaningful to us as programmers. And things that aren't semantically meaningful to the program's dynamic semantics, like comments, really jump out certain meanings for us. So if I see a variable named error, then I know it's an error path intuitively, even though I can alpha rename the program so that it was named foo or something like that. But there is a kind of independent semantics that goes into our brains that we use as a social process, and perhaps machine learning can kind of track these, less rigorous semantically features. But anyway, so there's a lot of things in comments and syntax that matters, even though they're not connected directly to the semantics of programs. Okay, so let's go over this, right? So here's some examples of some syntax usefulness. So, right, I'm looking at this code base and I'm trying to figure out where the error paths are. Like, I immediately look at error in these identifiers and I'm like, there they are, Similarly, I could see that most of the time these error paths are happening inside of conditionals and that I have a long distance to my OK path at the end. So it's pretty typical in C code bases that you'll see like go to out, where out is some label at the end of a C function. And all of the valid code goes there, so if something happens earlier, it goes to that. And I could arbitrarily rewrite this so that this return was at the beginning of the function, and then I had a go-to that goes all the way back up to some label, right? It's like it's semantically equivalent, but we don't do this, right? We write code in a certain structure. So this is one of those things where learning the idioms and syntax of how people actually write C matters, and especially when we think about specific code bases, right? So we want to look at like project-specific features per code base. So there's like 3 places we can look for project-specific idioms that are common to us anyway. One's directly in return expressions. So what kind of returns are we seeing often in a project? What condition often gets checked before return expressions across projects? and then what function calls can happen if that condition passes. Okay, so let's give examples from HTTPD. So very often you'll see directly return one of these two macros here, AP nobody read, or AP filter error. And basically these just immediately jump out when you see a return of this, that you know that this was an error path if you were looking at it just visually. Similarly, if I see something that's like in this code base that's like get this field from this struct and check if it's equal to HTTP bad gateway, it's like, okay, I know that if this is the check, then inside there's going to be some error handling code. So this is an error path. And finally, if these functions are called, so if I'm calling some kind of error logging function, then automatically, like if you see a return nearby, then it's probably an error path. So these are things that like, are syntactic, but you can directly kind of, if you have enough training data, see that these are the error paths, right? So what are the advantages of these project-specific features? So if we want to look at just like statistical measures, we can see that we get much lower p-values, which is good. Much higher chi-squared. So this is saying that all these project-specific features that we learn are quite relevant. And I like a more visual kind of intuition. So this is a visualization of like how our data looked if we were trying to separate error paths from non-error paths. And here at the top and on the right, basically you can see that it was hard to clearly separate this data. It's like very muddled together when I was only using the universal features. But when I added project-specific features, right, we have a much clearer, easy separation here. Like I can visually draw lines to separate these paths, those path predictions. Okay, and so that was gained from this two-phase learning where we learned this project-specific idioms. And what's really nice is that you use it just like what I was talking about with the global model earlier. So like if I want to train it on a new code base, I just kind of throw the code base at it, and it'll automatically kind of give me new classifications because it automatically generates new labeled data for you. So I can just kind of arbitrarily throw what I want to and not have to label anything myself. So this automates the process of adapting this approach to new code bases a lot. Okay, so the question is, why is this learned knowledge transferable? Right, so I have like maybe a limited set of C projects that I trained on for like my core model, and then later I'm throwing it at all these different projects which might have completely different idioms. And so if I just look at the features for this, it's like, okay, well, actually, I see that if I look at these two rows, that they're quite similar. There's only a 4 versus a 5. And if they're both indeed the things I'm looking at, error paths, then you can see that like the structural similarity of the code just really makes it easy to transfer to a lot of C code bases. And that in C, that there are a lot of idioms that are used commonly, which makes this okay. So we went through and we decided to study some large applications and get these error specifications out of them. So I've just been talking about how the machine learning works to classify whether something is an error path or a non-error path, but we needed to actually get the error specification out of that. What's interesting is that there's like a lot of error and non-error ranges that can overlap. So return 0 is commonly both an error and a non-error value in code bases, and I think that seems a little bit natural. But there's also some things like libgcrypt uses positive error values pretty much exclusively, other than -1 and 0. And also, like all of its non-error values that it's returning from these functions are also positive. And then across different projects, we can see that other ones might only use negative error codes. So across projects, actually, it's not commonly agreed upon whether error codes should be positive values or negative values among C developers. So it can be pretty ambiguous when you start learning a new code base, basically, like what kind of error codes you're looking at. So this tool could really help you ahead of time see what you need to handle when you get a new specific project. Okay. So let's talk about our accuracy at finding whether or not something is an error path. All I wanted to get at here was basically that without these project-specific features, our precision wasn't that great. So we were about like 79%, and that jumped to 91%. So that shows that like having the machine learning basically go and learn the idioms of like the syntactic things that appear in these different code bases actually gives you some pretty big wins as far as like boosting your accuracy of your classification. And then the next thing is I wanted to compare it to a previous tool that was used for getting error specifications and basically how accurate the specifications were. And in general, our approach was did better. And the nice thing is that the other approach previously could only be done on library codes, where you could basically find new C code bases that called all these different functions from these libraries. And they would use that in some constraint-based analysis to get their error specifications. Whereas we could throw it at just like any application, so we could throw it at the Linux kernel and other things that weren't libraries that had to be called. So it's a little more flexible. So this was interesting. So we decided that, it's not just, you could get these specifications, but we want to find bugs with them. So we made a little tool that's basic, where we do some constant folding and some other things. But basically we can see if our error specification differs from like our constant folding on certain functions to see if like their return value is different than what our specification says. And we were able to basically find a bunch of known bugs already. So we looked through bug reports for like the kernel and other things, and said that our tool basically found these bugs and could have prevented them ahead of time if the programmers had these error specifications. But also we found 9 new bugs and reported them, and we're waiting to get back on all of them. But some of them might be actual bugs. So this shows that you can really use this for something useful as far as, and I think we could extend this to a static analysis that will work pretty well. So just to conclude, basically, the lack of native error handling support in C makes it easy for programmers to handle errors improperly. So if I don't check for very specific negative integer values, I might cause a bug in code. With generated error specifications, basically I can give you just some documentation ahead of time to make sure that you check against, so you can say, okay, I'm actually writing my code correctly, and I'm cleaning things up based on these error codes. With two-phase machine learning, we were able to really classify non-error versus error paths in large C applications, things like the kernel. And that basically, it's nice in that we can start throwing this at more and more C applications, and very little is involved from people who want to do that. And then basically with these error specifications, we developed a very basic tool that I'm hoping to extend, but that can find new bugs in these existing important code bases. And in general, I'm interested in the future. Right now, we have these syntactic features as a universal things. I think that maybe only semantic features, things that are very related to the execution behavior of programs, should be trained on for a universal model. And then syntactic features should all be analyzed specific to code bases, especially because certain syntactic things can change a lot. What kind of identifiers you use, et cetera, across different code bases. So that's future work. All right, questions? Okay. Sure.
Yeah, otherwise it doesn't go to the recording. So a bit more from the practical part. Could you elaborate a bit on the tool? So basically you now have higher precision, but what does it entail in terms of time or memory?
Time a bit, but yeah, so. Yeah, so the question was about whether like getting these project-specific features, whether that required more time, basically. Is that what you were thinking?
How practical is the tool in terms of like how long does it take actually to run the
Yeah, so we have in the full paper some evaluation results. So I don't want to, I guess, like misremember that right now. I don't have them in my slides. But it was practical enough. I want to say it was like thousands of seconds for certain code bases that were very large. So it was still, I think, within reasonable, especially if you're analyzing something like the Linux kernel. And there were some implementation details, I think, that could have been approved that would have given us big gains if we did them. So I think those numbers could be lowered. So, but anyway, I think it was like 3,000 seconds for one of the projects, which is, I think, what, like 5 minutes or more. But anyway, I think that's practical when you're talking about scale, I guess. Oh, wait. Yeah.
Hello. Okay. You said that you're using essentially machine learning to do like semantic analysis on people's coding styles. So I guess my question is, do you think that like natural language processing or other things could be used more effectively than like machine learning, where you're sort of just like throwing statistics at it, I guess?
Maybe. I think as far as like NLP techniques, maybe for comments or something like that could be very useful, right? So if I have like a doc string or some comments about like this right here, if you see this, this is an error, could be very useful, I think, for helping extract things ahead of time, assuming your code's well documented. Other than that, though, I'm not sure off the top of my head. I mean, I think that the machine learning was just good for like seeing like maybe a certain syntactic thing enough times and associating it with errors, and it could just kind of recall that. But yeah, I do think there is room. It'd be nice if the whole future of the world was like illiterate programming. Then we could like really throw NLP at it. But yeah, I'm not sure how much you would get. I think it would depend on the quality of the code base and certain other things.
Hello, network. And I would like to ask if you have considered these scenarios in especially Linux kernel. How about some paths all go to the same place and just return a variable, and before go to, it was set to a constant value, something like that. Can you handle that?
I believe so. So you're talking about like you have something set that determines whether a bunch of go-tos go to one place?
Yes.
Yes, there are certain very like dynamic idioms that are hard. So like if you have like a function pointer or something that's used in like returning like an error path, like if you call a function pointer later or something like that, and then that produces an error code, we don't do very well for that because that's obviously a very dynamic kind of behavior. But I think like as far as like setting something to a constant before a bunch of go-tos, I think we were working pretty well for that.
Okay, thank you.
Yeah.
Hi, good
Hey,
talk.
Thanks.
So I'm just wondering if you are able to detect in the error specifications that you produce, not only the case or the idiom of returning an error value, but the case of like setting a global error flag or something like the error no number thing.
Right. So as far as like setting like global errors for handling later, I think that's a bit out of scope from what we're doing. So I would like to do that. But yeah, so for now it's local to like your function can return specific error codes, and we have to make sure those are called. But like very things like setting something like in a global struct or like setting some global constant to something, that's a bit harder to look at, especially because there might be like in another part of the project even that's like included and things like that. So those become more difficult, but of course they're very useful.
Okay, let's thank the speaker again.